Okie dokie, chemists, let's get started. So, tomorrow, Friday, is recitation 9, second to last attendance-based recitation activity, where you will review electrochemistry concepts with your TA. But then the following Friday is midterm 4, which covers all of chapter 19 and all of the chapter 20 stuff that we're going to cover today. So yeah, we will finish midterm 4 material today. And so with that, I will still plan on holding a midterm 4 review session at the same time, Tuesday at 5:30. I just haven't posted it because I haven't made it yet. Yeah, but it will still be on Tuesday at 5:30, typically, you know, in this room, all that stuff. Okay, so, all right, so let's review some concepts from electrochemistry, because maybe we were moving kind of fast, but I want to kind of review these concepts because it's these underlying concepts that are important for the coming parts of the chapter. And I'll point out that some of these questions, you know, these are kind of the low-hanging fruit kind of questions on the exam, but it's only a straightforward question if you understand what the question's asking. So let's work through these examples. So I have a redox reaction here. A cation becomes A solid, B solid becomes B plus cation. So in this reaction, A plus is being what, B is being what, and then can we relate that to the corresponding agents, right? Like reducing versus oxidizing agents. So my strategy here, basically all 4 of these questions are the same thing. It's assessing the same thing. Can you assign oxidation numbers, and can you relate, track how an element is changing its oxidation number, or how is it gaining or losing electrons? So my strategy for all 4 of these questions is let's get the oxidation numbers of each of the substances here. They're just generic elements, but basically it's charge. To get oxidation numbers. So we see A is going from +1 to 0, and B is going from 0 to +1. So we see A is being what? Reduced. Yeah, so A plus is being reduced. Notice how I'm pointing to the reactants. Those are the things reacting. I'm not pointing to the products here. So therefore A plus is what kind of agent? Oxidizing agent. So then therefore B, its oxidation number is going up, so it's being oxidized, so it is a reducing agent. And again, all 4 of these questions basically assessing the same thing. Can you track oxidation numbers and then assign them appropriately? Reduction means gaining of electrons, so your oxidation number is going to go down. That's what you want to look for. Oxidation means loss of electrons, so your oxidation number is going to go up. That's what you look for. All right. So let's assign numbers to this now. So here, you know, that was a conceptual question of just identifying things, but what if I give you numbers? So note, these 2 half reactions are both in the reduction form. When you go to a textbook and look up reduction potentials, they'll always be in the reduction form. But in a redox reaction, something's always reduced, something's always oxidized. So we need to identify, okay, whatever is reduced, that is going to be at my cathode, while whatever is being oxidized, that is at my anode. So simply to calculate the overall cell potential is to take the reduction potential at the cathode and subtract the reduction potential at the anode. So the subtraction is what does the flipping for you. So you don't need to flip the reaction, because what we'll talk about in a minute is that a reduction reaction is the opposite of an oxidation reaction. But regardless, to calculate each cell of this reaction, we take the reduction potential at the cathode, subtract the reduction potential at your anode. So in this example, it's going to be A plus, we just said, is our cathode. B plus, or B going to B plus, is our anode. So in this case, it is 1 minus 0.4. So our measured cell potential, oops, I'm sorry, slippy fingers, is our measured cell potential, if this was at standard conditions, would be something like 0.6 volts, something like that. As long as you identify your anode, your cathode, do cathode minus anode to calculate that cell potential. Okay, so that's calculating cell potential using textbook values like what you would find in a table value. I'll draw a comparison here. So I keep saying, like, you know, it's cathode minus anode, but both of them are in the reduction form. The reason is because when you go to a textbook, you'll only find reduction values. Kind of like if we're talking about weak acids, like acetic acid, HF, like sulfurous acid. If we're talking about weak acids, we always find their Kas. But what if you need their Kb? Will you ever find the Kb of F minus? No, you have to figure out what it is using the Ka. So it's the same thing here. You'll always find the reduction potentials. If you need the oxidation potential because of you're talking about an anode, so an oxidation reaction, you're not going to directly find that oxidation number. But what you do have is the reduction value and the reduction reaction. But if you recognize that a reduction reaction is an oxidation reaction flipped, you can calculate those necessary values. Okay, so let's interpret these values a little bit more before applying that knowledge that I just mentioned. So here, let's look at these reduction potentials. So for A, the reduction potential for A plus to whatever is 1. And then B plus to B solid is 0.4. So the magnitude of these values tells us how spontaneous these reactions are. So typically what we're looking for are positive voltages. So a positive voltage means that the reaction is spontaneous. So for A plus to A, that's a fairly spontaneous reaction because E red is a positive number. Versus B plus going to B solid, it's still spontaneous but not as much. So can we compare these values and interpret it to make some type of conclusion based upon these reduction potential values? A plus is what? More or less easily reduced than B plus. What do we think? More, yes. And here's the reason. Let's do a different color. More. Because what we looked for is that the reduction potential of A was more positive. All right, so if we're talking about how easily something is reduced, let's look at the reduction potentials and look for the most positive one. That's kind of the thought process there, all right? So we look for the most positive reduction potential. The more positive it is, the more easily oxidized that substance is. Okay, or conversely, we can talk about ease of reduction, or we can talk about oxidizing agent power. All right, so A plus would be what? A better or worse oxidizing agent than B plus. It would be better. All right, because things that are easily reduced are also going to be better oxidizing agents. So it's basically asking the same question. Things that are easily reduced, or they're stronger oxidizing agents. Okay, so that is the reduction form. Kind of like how Kas were easy and Kbs were a little hard. Reductions are easy. Oxidations are a little harder because we have to think, oh, oxidations are the reverse of a reduction, and typically they're not given. So let's review it. All right, so here are the same two reactions, A plus to A solid, B plus to B solid. So those are reduction reactions, both of them, because the reactants are gaining electrons. But if you look below those, I've written two new reactions. These are oxidation reactions. You're taking the solid, and that solid is losing an electron, right? But what you see here is that this first reaction is the same as this reaction, but flipped. So just flip it. So see how a reduction reaction is just the opposite of a reduction reaction is the opposite of an oxidation reaction, all right? So just like how Ka times Kb is equal to Kw for a conjugate acid-base pair, which you guys feel comfortable with after your midterm 3 scores that they're so high. Same idea here, that if you flip a reduction reaction, you get the oxidation reaction. What do you think the value is for the voltage for the oxidation reaction if we flipped it? So it's not going to be 1, it's going to be -1. Yes, it's -1. So -1 volts. For A, But notice it's a negative sign now, but see how this is the cell potential, or so the potential for the oxidation reaction. And then for B, it's going to be the same thing, negative 0.4 volts, right? So if we look back at that original equation, this one, all right? If we look back at this original balanced equation, these are the two reactions that are involved in this balanced equation. A plus goes to a solid, so this one. So it looks like we are using this half reaction, this exact half reaction. And then we are adding, or B is changing, it's being oxidized, it's going to B plus. So we are actually using this last equation, all right? These are the two exact equations that are involved in the full balanced redox reaction. Here is the reduction reaction, here is the oxidation reaction, and here are those two potentials in the reduction form and the oxidation form. So what you see here is if we add these two reactions as is, then yes, we can simply say, oh, the cell potential for this overall process is the reduction potential plus the oxidation potential, and see how it becomes 1.0 plus negative 0.4. See what I mean by the negative sign with the original cell potential equation is E cell, you know, cathode minus anode, but both of them have to be in the reduction form. So cat minus anode. That negative sign does the flipping for you. When we flip a reaction, we also flip the sign of E. So don't double flip it. Like, I know that an oxidation reaction is happening at the anode, but when you use cat minus anode, just keep both of those values in the reduction form because that's what you're given on a table, all right? So, but what I wanted to show here is that oxidation half reactions, they are the opposite of a reduction half reaction, all right? So I'm just going to move this. Oh, we'll just keep it. It's fine. Okay, so we flip a reduction reaction to get our oxidation half reaction. We flip the sign of E, but also note that the identity of your products and reactants change. In a reduction reaction, the cations are the reactants, but in the oxidation reactions, the solids are the reactants. So you got to be careful about language here, and you want to make sure you pick the right thing. So here, let's interpret these based upon these numbers. A solid is what? More or less easily oxidized than B solid. What do we think? So since we're talking about oxidation, which reactions should we look at? The reduction reactions or the reduction values or the oxidation values? We want to look at those oxidation values. So what we're looking for are oxidation numbers that are high, very positive. So that means A solid is what? More or less easily oxidized than B solid. It's actually less because it's more negative. Yes. So there's a couple ways you can do this. You can either, calculate the oxidation values, or you can recognize, okay, the more positive your oxidation values are, that will also mean a more negative reduction value. That's what you want to be looking for. Kind of like opposites, like Kas and Kbs. Okay, so if A solid is less easily oxidized, that means it is a worse reducing agent. B is the better reducing agent because it's more easily oxidized. It has a more positive oxidation potential, or you can think a more negative reduction potential, right? So that is looking at reduction half reactions, oxidation half reactions, and how we can't understand that language. So hopefully that clarifies things. So let's put it all together with a different generic reaction. I have two substances. So put it together where we utilize what we just learned. Okay, I have two things, X and Y. So both of these are reduction reactions. I can tell because electrons are being added. So the first question, which substance is the most easily reduced? So what are we looking for? We're looking for the most positive number, but the most positive number within the reduction potentials, right? So we can see, all right, which one's the most positive? Okay, it's the second one. But then what is being reduced? What substance is being reduced? Is it Y2 plus or Y solid? It's the 2 plus. So this is my answer. because it is the reactant in the reduction reaction. I'm asking you what is most easily reduced. Or conversely, I could ask the question and the answer is still the same. What is the best oxidizing agent? That is the exact same question. A good oxidizing agent is easily reduced. So I don't want you to take up more space in your brain. All right, I want you to associate those two statements with one another. They mean the exact same thing. So whether we ask you what's the best oxidizing agent, I'm actually asking you what is the most easily thing reduced. So then you can relate it, okay, I'm looking for the most positive reduction potential, right? Save room in your brain. Those are the same question, they have the same answer. So let's think about it opposite now. Instead of easily reduced, we want what is most easily oxidized. So what kind of value are we looking for? A very positive oxidation value. But are you given oxidation values? No, so the most positive oxidation value is going to have what kind of reduction value? Negative, a very negative reduction value. So that means, okay, here this is the most negative reduction value. It's going to have the most positive oxidation value, but which thing is being oxidized, X plus or X solid? X solid, because in an oxidation reaction, it's the opposite of a reduction reaction where the products now become reactants. Yes, so it's X solid is doing the oxidizing, all right? So again, most easily oxidized is the same thing as saying what is the best reducing agent. You are looking for what is easily oxidized. So again, you're looking for the most positive oxidation number or most negative reduction value, but make sure you point to the right thing. All right, so hopefully that clarifies things so you can do the homework that will most likely be due here soon. Okay, and then you can look back at these questions that we did earlier for comprehension. Okay, so let's move on to the last part of chapter, the middle part of chapter 20 where K is back. Okay, big K, equilibrium constant is back, all right? So these last two sections, this is on midterm 4. The last 3 sections, this is on the final. We'll still finish this before midterm 4, but I want to emphasize that this is not on being assessed on the next midterm, but it is assessed on the final exam. So up in this chapter, we were always looking for positive potentials. Positive cell potentials, positive reduction potentials means the forward reaction is spontaneous. Spontaneous. That should sound familiar. That came from chapter 19. So if we're looking for positive cell potentials, what were we actually looking for all this time? Delta G was what sign? Negative, yes. So in an instance where E is positive, delta G is negative for that case. It's still all true for any spontaneous reaction. If delta G is negative, what must the entropy change of the universe be for that thing? It should be positive. So all of this is related to one another. It's all going to come together. Okay, yes, all right. So let's just talk about it and talk about cell potentials. But actually, before I do that, I need to describe what voltage is. I know that we've been, most of the time talking about energy terms, but voltage is something new that we've just introduced in this chapter. So what exactly is it? I like to think of it as an energy difference that's specific to redox reactions. The analogy can be like a waterfall. So voltage drop is like how tall your waterfall is, right? It can be like really, really big, really, really small, where each water droplet is like an electron. So each of those water droplets falling has the potential to do some type of work because of that potential energy, that distance that water droplet is making. So voltage is kind of like that energy difference, the height difference in a waterfall. Waterfalls, you can put like a wheel there and you can make it do work, right? Like flour mills basically were run out of rivers through moving water. So that is essentially what voltage is for different systems. Depending on what the identity of your cathode and anode are, you can have different height waterfalls. But in terms of electronic devices, voltage isn't the only measurement we have. If you look at any one of like your digital appliances or whatever, you're going to see both a voltage and you'll see a current. So current is different, and it's actually completely different from voltage. Current is like how wide your waterfall is. It's how many water droplets move over the waterfall at one time, where voltage just says how far it drops. So current is like, okay, do you have like a very skinny single stream waterfall, right? Or do you have a really, really wide waterfall that tons of water is moving over that hill at the same time? So that's what current is. Current, if you know, electricity is one of the things that scare me. Current is what kills you, not voltage. Current tells you how many electrons, how many water droplets are moving through your wire at any given time. So if the current is really high, you can be putting a ton of electrons through your body if you become part of the circuit, and that's dangerous. But it's the current. High current is what kills you, not voltage. So low current, like you could have like something with a really crazy voltage but a really low current, and it wouldn't be as dangerous as something with a really high current. So how current, current is measured in amperes or amps. We'll talk about it later, but what's important here is that we can convert from time to amps using a constant called Faraday's constant. So Faraday's constant F for Faraday, we give you this value, but Faraday's constant is a number that's right here, all right? So 96,000 coulombs per mole of electrons. So we can't measure electrons. We can't count electrons because they're too small, but what we can do is measure charge. So Faraday's constants allows us to make a relationship that we know how much a mole's worth of electrons possesses in terms of charge, because they're negatively charged. 1 mole of electrons equals a charge of 96,485 coulombs. All right, that's what Faraday's constant is, and we'll use it a couple times here in our Gibbs free energy calculations, and it'll come up again at the end of the chapter. All right, so yeah, we can't count electrons, but we can measure charge. So if we know the charge, we can back calculate to, okay, how many electrons are involved in this process. And that'll be important to us a little bit later. Okay, so I mentioned before that we were always, all this time, looking for positive cell potentials. All this time, those positive cell potentials also meant negative Gibbs free energies for that reaction. That's what you were actually doing. And then conversely, it means positive delta S of the universe, because that's the second law of thermodynamics. So the reason, we won't really talk about entropy anymore. It's all about Gibbs free energy, since that's all about the reaction. So the reason that this relationship is here is we have this new equation that relates the Gibbs free energy for a reaction to its cell potential. So we see here that the cell potential for some type of redox reaction is equal to negative n, where n is the number of electrons in that process, times Faraday's constant times E. So this is where you clearly see that, oh, positive values of E cell give negative values of delta G, both explain spontaneous reactions. So here's the new idea for chapter 20. We just said, okay, Gibbs free energy is related to the negative of your cell potential. But here's the thing, let's bring back chapter 19. Chapter 19, we said, oh, if we know the Gibbs free energy for a chemical reaction at standard conditions, we can also calculate K, the equilibrium constant for that reaction. We were able to do that. That's what we did in chapter 19. So at standard conditions, you can look up book values, get delta G naught, and calculate K for that reaction. Depending if it's very spontaneous in the forward direction or not, you might have big or small values of K. So if delta G is related to E, delta G is related to K, wouldn't it make sense that the cell potential is related to K as well? Yes, because they're related by delta G. And so now we have this new equation that can relate the equilibrium constant to your cell potential given a chemical reaction where you know its properties at standard conditions. And so this slide is meant to highlight and overview all of the equations we have to work with in this chapter and how they're all interconnected. Note that I have two sets of equations. These equations we typically use at standard conditions, meaning use the table values, the book values, products minus reactants, cathode minus anode. That's where you use these values, these equations, all right? Cathode minus anode, I'll add, products minus reactants, all right? All of these reactants are measured at standard conditions. These relationships are related to standard conditions, so we can use those textbook values, all right? And notice how all of these at standard conditions properties have these knots present, okay? That is what standard conditions mean. So typically 298 Kelvin, 1 molarity of everything, 1 ATM of everything, right? Versus we're also going to talk about things at non-standard conditions. So notice how these values do not have knots on them. That's not a mistake. So when there's no knot, when there's no little circle there, we're talking about non-standard conditions, so Q conditions, conditions that are not at K equilibrium conditions. So what we'll see here is that back in chapter 19, we were able to calculate Gibbs free energy at certain conditions to predict which way a reaction goes based upon its free energy at regular, its normal free energy, plus RT ln Q, where Q is the conditions at that very moment that I want to predict does it go left or right. We can actually do the same exact thing for the cell potential of our electrochemical cell if we're not at standard conditions. So if you squint in your eyes, these two equations, they're actually, they are the exact same, where this is our measured cell potential is equal to our normal cell potential at standard conditions minus some factors log of Q, the actual concentrations present when we're not at standard conditions. So you see that these two, the boxed equation and the delta G equation, they're very, very similar to one another, where we're calculating something at non-standard conditions, but we need that standard condition value first, all right? We need that first. And we'll do a lot of examples relating all of these together. Okay, so let's talk about the significance. Why do we need to talk about electrochemical cells at non-standard conditions? Well, it's because the moment we start a reaction, we can start at standard conditions, so 1 molarity of everything, but as soon as we turn on our battery or start using it, it starts to deviate away from standard conditions the moment we turn it on. So let's think about this. Remember, a reaction is happening, right? So here's my balanced redox reaction. Zinc is being oxidized. It's my anode. Copper is being reduced. It is my cathode. So at standard conditions, zinc 2 plus is 1 molarity concentration. Copper 2 plus is 1 molarity. That's at standard conditions. So when you go to the book and you do cathode minus anode and you get 1.1 volts, you'll only measure 1.1 volts if Q is equal to 1. Or you will measure 1.1 volts if you are at standard conditions. So, we did this demo here, right, where, I hooked up this voltmeter to electrochemical cell that has copper, 1 molarity, zinc, 1 molarity. So if I hook up the cathode and the anode, it should measure 1.1 volts, where instead we can harness the energy to make it do work for us instead. But this would measure 1.1 volts because we have 1 molarity of each of these things. But as soon as we deviate away from standard conditions, we will not measure 1.1 volts. We'll actually measure something else. But let's think about that why. All right? So let's look at the Nernst equation. So this equation is the Nernst equation. All right? You use this equation when you want to calculate the cell potential at non-standard conditions. So you might be wondering, what is that 0.0592 volts? So this first equation is actually the Nernst equation, where there's a factor of R, T, and F, but R is a constant. T, if we're at standard conditions, it's 298. F is a constant. So what we just did is just combined it all because they're all constants, and made it easy just dependent on n, because that's the only thing that can change. So these two equations are the exact same. We just combined all of those constants for you at 298 Kelvin. So this is the equation we use when we're at non-standard conditions. So at first, this was at standard conditions, 1 molarity of everything. But let's think about this. So when we start our reaction at standard conditions, Q is equal to 1 initially when we're at standard conditions. So Q equals 1 right there. And that's why we measured 1.1 volts. So let's think about this mathematically. If Q is 1, log of 1 is what? 0. So that means at standard conditions, the cell potential you measure is the cell potential from the textbook. That's why standard conditions means standard conditions. Why we're allowed to just do cathode minus anode is because Q is 1 and this whole term goes away. All right, so that's why we're allowed to use those table values only at standard conditions. But let's think about how this reaction changes the moment we start running it forward. Remember, a reaction's happening. So as this reaction proceeds forward, as we start moving that little flag, how does the concentration of zinc 2 plus change? It gets, look at where zinc is. It's a product. So zinc 2 plus concentration increases. Yes, it's a product. In order to make electrons, you got to make product, right? So we're going to increase that zinc 2 plus. And then how does copper 2 plus concentration change? It decreases, yes. So if we calculate Q with time, how does Q change with time? Zinc 2 plus, this number, the numerator is getting bigger. Copper 2 plus is getting smaller. So how does the value of Q change? It, increases, yes, with time as the reaction proceeds forward. So if Q increases with time, let's erase this real quick. All right, so remember, E without the naught is what we're measuring at that certain time. So if Q is a big number, make Q bigger and bigger and bigger and bigger. If you take the log of Q and Q is a big number, this entire number that you're subtracting is also a big number. So as Q gets bigger, how does your measured cell potential change? It goes down. Yes, it goes down. Do batteries last forever? They don't. They eventually do what? They die. And why do they die? It's because you're converting all of your reactants to products. Q is getting big, and your cell potential is getting smaller and smaller and smaller until it approaches 0. It approaches a 0 once Q equals K, technically. So that's why batteries die. Yeah, you can just simply think, oh, it's because you're converting reactants to products, but it's really because we're changing the Nernst equation. So cell potential decreases so much that it approaches 0, all right? So, okay, so let's play around with the Nernst equation and how it's useful to us. So the idea is, here's the Nernst equation. In order to calculate the cell potential at non-standard conditions, weird conditions. Use the Nernst equation when you have weird concentrations that aren't 1, all right? But in order to use the Nernst equation, we still need those table values. E naught comes from the table values, from cathode minus anode. So you still need that value, but you're also going to add, incorporate how Q conditions are changing that value. Right, so we still need to do cathode minus anode, but remember that value is only valid at standard conditions. So let's look at this complicated reaction, but I've separated the two half reactions for you. We have this chromium compound, and it's reacting with iodide. So I give you the two reduction half reactions, but I need to figure out what the anode and the cathode are, because my strategy here is let's calculate E cell naught, meaning we just simply do cathode minus anode, use table values. But we need to figure out which one of these is the cathode, which one's the anode. So me, personally, my lazy way is to look at the simplest thing. And so to me, that's I minus. I minus starts with a -1 oxidation number, and it's becoming I2, which is a 0 oxidation number. So I minus is being what? Oxidized, so it is the anode. So if I minus is the anode, what must the chromium thing be? It has to be the cathode, yeah. But we can check it too if we want, but that one's a little bit more complicated because of that reactant with all those oxygens, but it'll still match. So the product chromium is +3, but the chromium on the reactant side, there's 7 oxygens, so that's -14, has to add up to -12. So the 2 chromiums have to add up to 12, or sorry, it adds up to -2. So the 2 chromiums have to be +12. So 1 chromium is what? Just one of them, +6. Yeah, so chromium is going from +6 to +3. So chromium is being reduced. So yes, it is the cathode. All right. Or you can just look at one of them, but it all checks out there. Okay, so we identified the anode and cathode. So you just do those 2 reduction values subtracted. So 1.33 minus 0.54. Remember, the negative sign does the flipping of the anode for you. So you get an overall cell potential of 7.79 volts. If we are at standard conditions, meaning we have 1 molarity of everything, we will measure 0.79 volts. But the follow-up question, are we at standard conditions? We are not, so we have to use the Nernst equation. But the Nernst equation still uses that 0.79 value, so we needed to do that first anyway, right? So looking at the Nernst equation and what we're given a bunch of concentrations. So it looks like we're able to calculate what Q is based upon these concentrations. We already have delta E naught, or we have the cell potential, the standard cell potential. We just got that. This is E cell naught. And the last thing we need is N, okay? So the last thing we need is N, and the easiest way to do that, instead of like undoing this reaction, what you can do instead is just look at the 2 half reactions. Look at the electrons and like lazy add them up and ask yourself, okay, if I had to add up these 2 reactions, but you don't have to, what is the lowest common multiple that those 2 have? It's 6, right? That you would multiply the second reaction by 3, so it's 6, and they cancel out. So N is 6 in this reaction. You didn't actually have to really do the work. You can just kind of look at the numbers. Or here's another trick you can do. So N is 6, meaning that there are 6 electrons involved in this process. Here's another idea. Look, there are 6 iodides. What total charge is right here? Total. -6. Those 6 iodides are becoming 3 totally charged neutral iodines. So iodide is losing 6 electrons. So there's the 6 electrons, just validating what you just got. Okay, so we have E naught, we have N, we just need to calculate Q. This Q is no different than the K expressions we've been doing before. It's just a little bit more complicated. There's lots of stuff here. So let's get this Q expression for this balanced chemical reaction. Remember, K is just products over reactants. So Q is just products over reactants. So my products, I have chromium 3+ concentration, but it's squared. Do I put anything else in my numerator? No, because everything else is a solid and a liquid. Very good. Next, the reactants are, we have that chromium oxide compound to the 1. H+ to the 14th power, dang, that's big. And then I- to the 6th power. All right. We have everything we need to calculate Q. You just plug in those numbers that are given here. So Q at these conditions given is something like 1 times 10 to the -5 molarity, and that's squared over that chromium concentration, so 2 molarity, H+ concentration 1 to the 14th good, so that's 1, and then I concentration also 1, so 1 to the 6. So simple enough, those 1s go away, since 1 to anything is 1, and we get that Q is equal to 5 times 10 to the -11. This is Q. Right, and that's the value we are going to plug into our Nernst equation. We have everything now, and it's plug and chug. So the cell potential that we actually measure in these conditions is equal to what the cell potential usually is at standard conditions, so 0.79 0.79, so we still need that value at standard conditions, even though we're not at standard conditions, minus 0.0592 volts, since we're at 298 Kelvin, N we got was 6, log Q, that value we just got, 5 times 10 to the negative 11. All right, and so you get that the cell potential at our non-standard conditions is a little bit higher than what it is at standard conditions, just because we've packed a lot of reactant in there. Packed a lot of reactant, so you know, our battery, produces a stronger voltage, all right? So yeah, we see that's a little bit higher than what it is typically at standard conditions due to the nature, due to the magnitude of Q, all right? Okay, so that's how we use the Nernst equation. Let's do another one where it's just opposite. I gave you Q, you solved for E. So how about I give you E, you solve for Q, specifically a component of Q. So in this question, I'm telling you the cell potential, the measured cell potential. It's the same reaction. We have the standard condition cell potential. We already know N. Let's calculate Q, because this question is asking you, what is the pH? pH is also what? The measure of H+. Yeah, so if you look at the Q expression, which concentration should we calculate? H+ concentration. Yeah, so once we get Q, we can figure out what H+ has to be to achieve that Q, because I do give you the concentrations of everything else. So this is just the same question but backwards. We're going to solve for Q and then solve for H+ given the rest of those concentrations. This one's a little bit trickier, but it's the same process. So here's my measured cell potential, it's 0.81 volts at these non-standard conditions, equals the regular, this is E cell naught, the table value, so 0.79 volts, that's usually what it is, minus 0.0592 volts over 6, that's N log Q. I'm going to solve for Q. All right, move some stuff around, so I think that's positive 0.02 equals negative all that stuff, log Q. All right, and then multiply both sides by 6, divide by negative 0.0592 to get rid of that coefficient. And so you get that log Q is equal to something like negative 2.2027. How do you undo a log? 10 to the, so 10 to the log Q, 10 to the negative 2.2. So that means Q is equal to 10 to the negative 2.2027. So Q is equal to, you put that in your calculator, you get a little number, 0.009396. Right, so this tells us the ratio of products to reactants present at these conditions to yield this voltage. So just plug that value of Q into the actual Q expression, right? So we said that Q is equal to products over reactants. I give you concentration of chromium 3+, of the chromium oxide thing, and of iodide. So we just have to solve for H+ in this case. So chromium 3+ is something like 1 times 10 to the negative 5. Don't forget that that is squared over the chromium oxide compound, so 2 molarity. I'm solving for H+ concentration. That's to the 14th power. And then I minus, thankfully, is just 1 molarity, and that's to the 6th. And so if you move, all of this is equal to that value, 0.009396 value we just got from manipulating the Nernst equation. Now it's just solving for Q. And so we are solving for that H+ concentration. If you move everything around, you get that H+ to the 14th power is equal to 5.3 times 10 to the negative 9. Okay, how do I undo a 14th power? Should I spend time looking on my calculator where the 14th root power is? No, don't waste your time on that. To undo that to the 14th power, you take both sides to the 1/14th. 1/14. To undo it. So that means H plus has a concentration of, oh, it's somewhere in the corner. Yeah, right there, all right? Is 0.256 molarity, and then if you negative log that, you get a very, very acidic pH, so even less than 1, pH of 1 that we see, all right? So yeah, so that's the pH we need given these concentrations to give this Q value that will yield this measured voltage, all right? And we use the Nernst equation to make that relationship between the measured voltage that we actually read and the concentrations of products to reactants that are actually present in that solution. Okay, so let's do another one. All right, so the main thing here is, and it's just like delta G when we calculated delta G at non-standard conditions. Even though we're at non-standard conditions, we still need the standard conditions value to calculate the non-standard conditions. Just like delta G, we do the same thing here for cell potential. We still need the cell potential at standard conditions to use the Nernst equation, even though what we're calculating is at non-standard conditions. So let's look at this question and, again, be very cognizant of what the question's asking. Am I at standard conditions? Am I allowed to just use the book values? Can I just do cathode minus anode? Or do I have to be a little bit more sophisticated and use the Nernst equation? So here, I'm telling you, here's a redox reaction. We are at standard conditions. So can I just use book values? Can I just do cathode minus anode? Yes, because I'm at standard conditions. That's good because I want you to calculate delta G, not, meaning at standard conditions, and K. So looking at these equations up here, as long as I calculate E cell for this chemical reaction, I can use this equation of delta G to calculate delta G using the cell potential that I calculate, using book values. Once I have delta G, I can then just use chapter 19 concepts and calculate K with that delta G I just got. So basically, this question is use the information given, the reduction potentials, the table values to get the cell potential at standard conditions. We're allowed to use table values because I explicitly state we're at standard conditions, so we have 1 molarity of everything. So if we look at what's happening in this reaction, silver is being what? Oxidized. So it is the anode. So therefore oxygen has to be the cathode. Yeah, you can go check if you want, but I don't feel like it, right? So there's the cathode, there's the anode, so that means my overall cell potential at standard conditions is 1.23 minus 0.8. And so we get a cell potential of 0.43 volts. So you set this thing up, it does run spontaneously because E cell is positive. So let's now relate this to Gibbs free energy and K. If this reaction is spontaneous, just guess, what is the sign of delta G? Negative, yes, all right. And then if delta G is negative, how big do you think K is? Is it gonna be a big number or a small number? If the forward reaction is spontaneous? Big, yeah, if the forward reaction is spontaneous, you're gonna make a lot of product, so K is big. So that's what we should anticipate here. All right, so we're gonna do delta G equals negative. So this is part 1, we're gonna do delta G first. NFE. All right, we have F, we just calculated E, we just need to get N. So looking at these two half reactions, what do you think N is? 4, yeah, 4 is the lowest common multiple amongst the oxidation and reduction reactions. So N is 4. And so we just plug things in. So negative 4 moles of electrons are being transferred. Faraday's constant is 96485 coulombs per mole of electron. And then E is 0.43 volts. Okay, those are units you've probably, a unit combination you've rarely seen before. Just trust me in that a coulomb times a volt is equivalent to a joule per mole. Delta G is a joule value. So we're calculating delta G. A joule is going to come out. So when we multiply all of this together, just take a leap of faith, a joule amount comes out. And so we see that that joule amount is negative 165.9 times 10 to the 3 joules per mole for this reaction. Again, it comes out as a joule, but usually this is a really big number. So like in an answer key or something, you might see something like negative 165.9 kilojoules per mole. But do remember that a coulomb times a volt is the equivalent of a joule when we use these delta G equations. So there's no need for additional converting here. All right, so that's part one. We got delta G. Now we want to get the Q for this reaction. And we were right. Look, delta G is a negative value. Cool. If we want to get K for this reaction, we're going to use the other equation, delta G equals negative RT ln K. And now it's exactly the same as chapter 19. We already have delta G. It's negative 165.9 times 10 to the 3 joule per mole. I like to keep it in joules because we're going to use R in this step. Delta G equals negative R, 8.314, times the temperature at standard conditions, 298, times natural log of K. We've done a bunch of these in the last chapter. So you got delta G. You know the temperature, you know R, so just solve for that ln K by taking E to the both sides. And so you see when you solve for K, what comes out is, yes, a very, very big number, 1 times 10 to the 29. So this reaction is very spontaneous. It has a positive cell potential, it has a very negative Gibbs free energy, and it has a very large K value, meaning products are favored. The forward reaction is very favored. So all of these ideas are coming together, right? So a small detail here, we were at standard conditions. So if we're at standard conditions, it means anything with a concentration. So in this case, H plus, silver plus, all of these things with concentrations are 1 molarity. So if everything is 1 molarity, Q is equal to 1 in this case at standard conditions. So when we use the Nernst equation, usually that log Q term just falls out and we just measure exactly what's at standard conditions. But what if we're not at standard conditions? Let's consider this same redox reaction. So here I tell you that the cell potential, we just calculated it, is 0.43 at standard conditions. But let's say we set up the cell so it's not at standard conditions. So Q is not 1, it's actually a different number. Let's set it up so Q is equal to K, right? So Q is equal to 1.1 times 10 to the 23. Calculate E cell at these conditions. So here we're going to use the Nernst equation. Okay, we are trying to calculate what is the measured cell potential. We already know what the regular standard cell potential is. We know the number of electrons transferred. I think we said, what is it? 4. Because 4 electrons, 1 electron there. So 4 electrons are being transferred total. And then Q, and I told you what Q is. So it's just plug and chug. But let's see kind of the consequence of this, what happens when you set up an electrochemical cell that's already at equilibrium. So let's plug it in. So the cell potential you measure is equal to 0.43, the normal cell potential at standard conditions, minus 0.0592 over N, we said is 4, log Q, 1.13 times 10 to the 29. Right. So before I used to give you concentrations. Here I'm just telling you that the ratio is equal to K. Okay, so you plug that in and you get that this number, if you stick that number in your calculator, you get something like minus 0.42998. So that number right here is really close to what? 0.43, isn't it? You subtract this in your calculator, what number are you going to get? 0. You get 0. You get 0. So 0 volts. So what did we just prove? That an electrochemical cell that's already at equilibrium produces no voltage. Let's think about what equilibrium is. Equilibrium is the forward direction spontaneous at equilibrium, is the reverse reaction. Both reactions happen, right? That's what equilibrium means. The whole point of a battery is we have, some energy storage, a portable energy storage device that's only spontaneous in one direction, and we're able to harness that energy. But when we're at equilibrium already, there's no push for one reaction to happen over the other. So if you have a battery that's already at equilibrium, that battery is useless to you. It is dead already because there's no chemical reaction to harness there. So yeah, what we just proved is a battery at equilibrium has no cell potential. It's zero. So therefore, what is the Gibbs free energy for a dead battery? Also zero, yeah. Because what did we say? Any reaction at equilibrium, its Gibbs free energy is zero. That the forward direction is not spontaneous, the reverse direction is not spontaneous. It's of no use to us for a battery, yes. Okay, and so this is significant when Q equals K. Okay, when your battery is equal to the equilibrium constant for your specific reaction, that battery is dead. Okay, so let's review everything and then do a couple more practice problems. All right. So just want to remind you that the last two chapters very much overlap. We talked about Gibbs free energy, spontaneity, related it to K, whether your forward or reverse reactions were spontaneous. And now we're also able to relate it to cell potential, right? Where what we're typically looking for spontaneous reactions. Back in chapter 19, we said when delta G naught, when the table value was very negative, it meant that the forward direction for that reaction was very spontaneous. That typically also related to a very large K value, because large K value means lots of products, means forward reaction is spontaneous. And now the new part is, if your cell potential is very positive as well, then your forward reaction for that redox reaction is also very favored, the forward direction. So all these three things are related to one another. Note that I have knots on all of those. So that means you go ahead and just use table values, or you do products minus reactants, because we're talking about not at standard condition, because we're allowed to just use those table values since they were all measured at standard conditions. But as soon as we're not at standard conditions, which for the most part, when we run a battery, we're not at standard conditions. So this is like 95% of the time. We're at non-standard conditions. We see that the values of delta G, Q, they change. But these values never change. These values are book values. They don't change. But when our reaction proceeds, we see delta G does change. It approaches zero. Because once we reach equilibrium, and that's what all reactions tend to do, is go towards equilibrium, eventually delta G will approach zero. This happens because Q approaches K for any chemical equilibrium. And then finally, E, your cell voltage, approaches zero, because that's when your battery finally dies, all right? All of these things are related, and again, your battery will die once you reach equilibrium, and there's no more spontaneous chemical process. So as soon as, this flag stops running, or like this little spinny thing stops running, it's probably because the concentrations in here are such that the cell potential approaches zero, right? All right, so, okay, all of those are related. So let's do a couple more. But I'm going to present them a little bit differently. They're still Nernst equation questions. They're just a little different. Okay, so let's calculate cell potential for this cell at non-standard conditions. So note how, I say E cell. It's not E cell naught. If it had the naught, I'd go ahead and do cathode minus anode. But so for this one, I can't simply do that. I have to do a little bit more. Got to do the Nernst equation because we're at non-standard conditions. All right, so we're going to use the Nernst equation. So in order to do that, I first do need the standard cell potential. I need N and I need Q. So I like line notation because it clearly shows you what the anode and the cathode is. You don't have to guess or figure it out with a balanced reaction. we always read line notation, anode on the left, cathode on the right. All right, so then you can easily calculate E cell naught, the cell potential at standard conditions, because I just said that copper is the anode and silver is the cathode. So when we calculate the cell potential at standard conditions, it's simply going to be 0.8 minus 0.34, so it's something like 0.46 volts. That is the standard, or the cell potential at standard conditions. But based on the line notation, are we at standard conditions? No, we're not. So we have to actually calculate Q and use the Nernst equation, right? So I did the flipping for you. Remember, copper is being oxidized and silver is being reduced. So I flipped the oxidation reaction and then added it to the reduction reaction, multiplied the reduction reaction by 2, and then here is our balanced redox reaction, right? Where I've made the number of electrons cancel. What is that number of electrons? N equals what for these two half reactions? 2, yeah, very good. All right, so I did the balancing for you, and this is important because you need the full balanced equation where something is oxidized and something is reduced to get the value of Q, or get the expression of Q. You need to figure out what is the reactant, what is the product, and you need to put them on top of one another. Because in line notation, it's not as obvious. But once you have the balanced redox reaction, now it is obvious. Copper 2 plus is a product, so it goes on the top. Silver plus is on the bottom, so it goes on the bottom. Or is a reactant, so it goes on the bottom. But what else is missing here? Squared, perfect. All right. So getting Q will allow us to use the Nernst equation. So now I just take the concentrations exactly what's in the line notation. Copper concentration is 0.5. Silver concentration is 3 squared. So Q is equal to 0.0556. It's not our answer. Now we need to plug it into our Nernst equation. So E, what we actually measure for this specific cell at these Q conditions, equals what the cell usually is at standard conditions, so 0.46, minus 0.0592 volts over N, we said was what, 2? Log Q that we just got, 0.0556. And so go ahead and do that. And so at these Q conditions, you get the voltage is slightly higher than typical, right? And then you can plug that voltage. I didn't know that this said calculate delta G as well. Oh, no, it doesn't. Okay, yeah. But if you wanted to calculate delta G, you would just do delta G minus NFE. We have E, plug in 2 for N, and you're good for delta G. Right? But the big idea here is that at these Q conditions, given the line notation and the concentrations given, we get a slightly different measured cell potential. All right, so let's do one more. That's a little bit different, again, using line notation. All right, again, Nernst equation, but this one's a little trickier. Because what is the identity of our anode? Copper. What is the identity of our cathode? Copper. Interesting. So, if we wanted to calculate the standard cell potential, what would it be? Yeah, so remember, it's always cathode minus anode. So you have a number minus the same number, always 0. So here I give you the reduction potential, but technically you don't even need it, okay? Because copper and copper are always going to have the same reduction potential. So the cell potential is 0. Okay. Yeah, so what that means is if you have, copper just hooked up to the same thing, copper, it's going to read a 0 potential if we are at standard conditions. But are we at standard conditions? No, the concentrations are a little bit different, so we have to account for that in Q. So this question is the exact same. We got to get Q, but it's a little bit trickier, okay? Because 2 reactions are happening and both of them involve copper. All right, so here's the best way to do it. At your anode, oxidation is occurring. So if you write the oxidation reaction for copper, it's copper solid goes to copper 2 plus and then some electrons. But I tell you in the line notation that this copper is 0.1 molarity. all right? So that's the concentration of copper in the anode, and copper 2+ is a product. And that's going to be helpful for us for Q, because Q, it's always products over reactants, but in line notation, it is not obvious what is a product and what is a reactant. So then we do the same thing for the cathode, reduction. I'm reducing copper 2+ by adding 2 electrons to make copper solid. This copper in the cathode, I tell you in the line notation, is 1 molarity. So notice where those copper 2+ show up before we add them, when we add these two reactions together. So if we're trying to calculate Q, Q is products over reactants. What number goes up top, the 0.1 or the 1? Which one is the product? Is the copper 2+ the product? It's the 0.1. So here it's the copper in the anode, so this one's 0.1 molarity, and then in the reactant side, it's 1 molarity. So we see for this cell, where there's a concentration difference, Q is equal to 0.1. All right? And so this is important because we're going to use the Nernst equation again. If we were at standard conditions and the concentrations were the exact same, Q is 1, so E cell would be 0. But in this case, we have a concentration gradient, and that actually does produce a very, very small voltage. So we just plug in that Q into the Nernst equation. E equals what the cell is usually, and so that's 0, minus 0.0592 volts. What is N in this reaction? 2. 2. So 2 electrons, they cancel. Log, we just got log 0.1. And so if you calculate that, you get that just with a concentration difference, you get a very, very small voltage, all right, about like 29 or 30 millivolts just by having a concentration difference, even if the identity of your anode and your cathode are the exact same. But the only way to produce a voltage is if the concentrations are different. If they're the same, Q is 1, and then your voltage is 0. So let's show the demo for this. This is called a concentration cell, all right? So that's camera. Boom. Okay, so here's the concentration cell. It's just copper. Oh, that's not calendar. Camera, okay. So here's my concentration cell. Okay, can you see that a little bit? Yeah? Yeah, okay. So this is the concentration cell. So basically, actually I didn't want to show you this yet. Okay, there we go. So how they set this up is they put concentrated copper at the bottom, copper 2+, that's why it's blue, copper 2+ is blue. Really concentrated on the bottom, and it's really dilute on the top. So that's why we call it a concentration cell. So right now I have the electrodes disconnected. So what voltage are we reading right now? Basically 0, yeah, because the circuit is not complete. So the weird thing is here, it's all copper. But what's producing the very small voltage is just a concentration difference. So let me just complete the circuit, and we'll see what happens. Whoops. Yes, so now are we reading something? Yes, we are. So we're producing a very, very small voltage just by having a concentration difference at the top and the bottom. So I'm going to try this for this. It didn't work in the morning class. So what's producing the voltage is the concentration difference. And so like a non-1 value of Q. What do you think will happen if I mix all of this up, if I shake it? So if I mix it up, won't the concentration throughout the whole thing be the same? So what should Q be when I mix it all up? Well, 1, and then E cell will be 0. So let's see. It didn't work last time, so let's see if it works. So if I mix it up, does it go closer to 0? I mean, yeah, it's getting pretty close because it's like now a negative number. So it's probably not calibrated very well. But yeah, we do in fact see that that number go down, that now that we don't have a concentration gradient, that it is not producing as big of a voltage like it did before when there was a concentration gradient. All right, so that is our concentration cell. All right, perfect. Okay, so we have like 10 minutes. So I'm going to talk about batteries because I think batteries are cool. Okay, all right, so also what that means, this is the end of midterm 4 material. All right, yeah, so now you are primed to prepare for midterm 4. So the last part of chapter 20 is all of the application of everything we just learned about redox reactions, and I think it's pretty cool because, I mean, electrochemistry, I think, and analytical chemistry is kind of the newest branches of chemistry. So new that, you know, Honda is investing billions of dollars into Ohio's, you know, infrastructure to build the new EV, the electric vehicle battery plant. Okay, batteries are very important for our future and the convenience that we use every day. So we'll talk about batteries and how it relates to things that we've learned about. I guarantee at least one person in this room will work for Honda in that EV plant in the next 10 years. Okay, so batteries. Batteries, they're very convenient, and all they are just convenient, portable, handheld electrochemical cells. Technically, this is a battery, but I don't want to put this in my pocket. Okay, it'll spill everywhere. But what a battery is the same thing. We're harnessing the positive cell potential for a certain spontaneous redox reaction and harnessing those electrons that are transferred during that event. But batteries are just more portable, right? So we're still talking about spontaneous reactions. So there's 2 big different types of batteries because we keep talking about, you know, spontaneous electrochemical cells. Once your battery reaches, once Q equals K, your battery is dead. But for all batteries, are batteries dead once they're dead? No. Some batteries you can do what? Recharge them. And so that's the big difference in classes of batteries. There's 2 types that we'll talk about: primary batteries, secondary batteries. Primary batteries, these are non-rechargeable. These are your cheap alkaline batteries. You go to the checkout lane at Target and it's like the $5 off-brand batteries that you can get. Those are alkaline batteries. You use them once, whatever, you put in your clock or whatever, and then when they die, you throw them out, okay? They're not rechargeable, and there's a reason. Secondary batteries are rechargeable, all right? Where you do the spontaneous reaction once, you plug it into the wall, you're able to get all of your reactants back so you can do it again, all right? And it's a cycle. But primary batteries, you can't do that, and there's a reason. And this is how I think of it. So a primary battery, you use it, you turn all of your reactants to products, all right? But then when you like plug the battery in, like plug it into like electricity, instead of B, your products going back to reactants, it becomes something else. It becomes C, and C doesn't do anything. But for a secondary battery, one that is rechargeable, when you use it, you discharge it, you turn A into B, your product, and then you plug it back in, and it goes straight back to A. And that's why it's rechargeable, and that's why you have this cyclic cycle, right? But in an alkaline battery, the cheap ones, primary batteries, you can't do that. And it has to do with their cheapness, too, all right? That they're just made with materials that aren't easily reversible. You use them once, and then they're dead. Okay, and then we'll talk about fuel cells in a little bit, but those are different. Okay, so let's look at 2 examples of batteries. Okay, alkaline battery. Again, these are your Duracell batteries, the normal Duracell batteries. All right, here's the electrolyte. Those are the voltages given by the manufacturer, and then the type. So alkaline batteries, these are primary batteries. These are your Duracells, whatever, all right? I've identified the anode and the cathode in an alkaline battery here. So let's calculate what is the standard cell potential given these values. So it's cathode minus anode. So I told you the cathode is 0.15. The anode is minus negative 1.28. And so we see that the cell potential for an alkaline battery is, what is it? 1.43 volts. but the manufacturer says 1.5. Why do you think that is? What? I couldn't hear you. Tolerance too, but look, but 1.43 rounds down, so shouldn't they report 1.4? What did we just calculate? We used table value, so what is this? Standard conditions. Do you think the manufacturer packs their batteries at standard conditions? No, they probably make it way more concentrated. All right, so the reason they don't match, and that was down here, is because the batteries that we actually use are probably not at standard conditions. They're not necessarily 1 molarity of everything. So these are going to be, the values are going to be a little bit off, right? Okay, so that's our alkaline battery. Lead acid batteries, these are what are in your cars, in your vehicles, okay? You want your battery to work when you start your car, you want your spark plugs to go off, but then you want it to be recharged by your alternator, right? For the most part, most conventional vehicles, we don't plug them into an outlet unless you have an EV, but with lead acid batteries for conventional cars, they get recharged by your alternator as you're driving down the road, but still it has to be able to be recharged. And so the idea here is these two half reactions are reversible in that if I apply an electrical current to this reaction, I can force it to go in reverse, so then it can go back in the forward direction on its own later. That is the difference between a rechargeable secondary battery, all right? So lead acid, let's calculate the cell potential here. Cathode minus anode again, so 1.69 minus negative 0.36. And so we get a standard cell potential of 2.05 volts, right? But typical car batteries are actually 12-volt batteries, right? So the reason that it's different here is that in a standard lead acid battery, there's actually 6 different cathode anode cells within it that are wired in series to give you that 12-volt boost that you need to start over your engine, because just a single of these redox reactions would not produce enough voltage to be usable in a vehicle here. All right, so a little side idea. So here, alkaline battery. Alkaline means what? Basic. So this reaction is balanced in what kind of conditions you think? Basic conditions. You can see it. There's tons of hydroxide. But lead acid batteries, they are balanced in acidic conditions. So we have two different types of batteries here. So I think it's funny when we talk about crusty batteries. You ever open an old device and it's all crusty on the inside, and you go to your friend, you're like, "Oh, careful, that's battery acid. Don't touch that. Wash your hands." Battery acid. Technically, is it battery acid in there? Nope, it's actually battery base. Yeah, battery acid is just in those lead acid batteries in your vehicle, all right? So we'll stop there because this is where I stopped at the 8 a.m. We'll talk about other rechargeable batteries because that's the future. Rechargeable batteries, we love that convenience. Remember, part 1 of the homework for chapter 20 is due on Monday.